Hello and welcome to another lecture of classical motion of a single particle. Now, in this lecture we simply continue our previous discussion of different interesting features considering the motion under a central force, and just during the last lecture where we really stopped, and after that we solved two small problems, we discussed two small problems, but exactly I mean like as far as the lecture contents or the discussion is concerned, we actually stopped by just stating the Bertrand's theorem. And Bertrand's theorem is a super interesting theorem which says that only two central force laws are possible where every single bounded motion is associated with a closed trajectory. Okay. However, you have to pay attention to the point that Bertrand's theorem does not say that every motion under these two force will always associate a closed trajectory. That is a wrong idea. So, Bertrand's theorem simply states that if you have a motion under any of these two forces and somehow you are guaranteeing that the motion is bounded between a r max and an r minimum, that means the motion, now you can in terms of the energy diagram, okay, for effective 1D motion, you know that you have two turning points, two well defined turning points at some finite r values, then only you can expect you can always expect a closed trajectory associated to that motion. Okay. Now, today in this lecture we will start more formally several discussing several features of the motion under an inverse square law of force. Okay. So, inverse square law is simply given by f of r, which is equal to alpha over r square, where alpha can be greater than 0 or less than 0. If it is greater than 0, it is repulsive force. If it is less than 0, then it will be an attractive force. Now, f of r is equal to minus k by r square can be definitely an attractive force if we claim that right from the beginning k is positive. Okay. So, we will throughout our study we will exactly use this convention that f of r is equal to minus k by r square and k is positive. Okay. We should write now the total energy conservation just to exactly analyze the motion, this Vr by r motion under an inverse square law. Okay. That is our first goal. So, for that we write the total energy conservation half m r dot square plus L over L square over 2 m r square plus the true potential energy phi r, or sometimes we also say, I should not deviate much from my convention, V of r. Okay. That is exactly equal to the total energy, total mechanical energy capital E. Okay. Now, L is the angular momentum magnitude, m is the mass of the particle, and this is known as the centrifugal potential, if you remember, which is indeed the cross radial, which is indeed a part of the kinetic energy and comes from the cross radial part of the velocity. Okay. So, this is the true potential energy, and both of these combined gives us something, I just denote by this color, V effective. Okay. So, or effective potential. Okay. And we said that in general when we talk in terms of the V effective, okay, or the effective one dimensional motion in a central force, we plot V effective as a function of r to analyze the motion. Now, for a inverse square law, what happens, I can actually write that f of r is equal to minus k by r square. So, V of r will simply be equal to minus integration f of r dr, and you can easily say that this is, so minus, there is a minus, there is a minus, that will go away. So, it will simply have k by r square dr, okay, and then you will have is equal to minus k by r plus some constant. Okay. Now, you can simply say that when r is equal to infinity, I make a convention such that my potential V at infinity is 0, and that actually makes this C to vanish, and simply your true potential energy will simply be minus k over r. Okay. So, that means for an inverse square law, the V effective is actually L square by 2 m r square minus k over r. Okay. So, that is the part we can use here. Okay. So, exactly this function we will now plot as a function of r here. Now, for that we just have to remember two things, that when r tends to 0, even before that we have to make some careful observation. So, in a true 1D motion, your displacement x can be positive and negative. However, here r is the distance from origin to the particle in spherical polar, or now in this central force case it is 2D polar coordinate system. So, this is simply the radial distance measured from the origin to the particle. So, it cannot be by definition negative. So, that is why the energy diagram in this, for this effective 1D motion will be only covering the first quadrant, okay, and where, I mean first quadrant, of course, formally saying the first quadrant and the fourth quadrant where r is positive. Okay. V effective on the other hand can be both positive and negative. Okay. So, this is my origin, and I can simply realize two things. One is when r tends to 0, then you see that this part and this part, okay, they have both of them, okay, are in the denominator, but with the different power. So, when r is tending to 0, so it is very small, it is a proper fraction. So, having proper fraction in the denominator is actually saying that it is always multiplied by a number which is greater than 1. So, when r is getting smaller and smaller, so this term is actually getting also smaller and smaller. Now, since this term is actually in the denominator of this centrifugal potential term gets greater and greater, and with respect to this term is not getting enough importance at this limit, and that is why when r is tending to 0, V effective almost behaves like L square by 2 m r square. So, that means some constant by r square and its nature. So, and this is with a positive sign. So, V effective starts like this. So, exactly at infinity, I mean exactly at r is equal to 0, it is at infinity. So, that is why it starts from a very high value over here, and then it decreases. Okay. Now, of course, you can understand then it decreases to certain value, and finally, this one also comes into play, and there is a competition between the values of this term and this term, and at some point both of them nullify each other to have a V effective which is 0, and then this term shoots again. Okay. And finally, what happens if you see, so of course, we know that it will decrease and at some time it will touch V effective will be equal to 0, that we know. Again we know that when r is tending to infinity, then this term will vanish or will how to say like drop off very quickly, because this is 1 upon r square dependence and here this is 1 upon r dependence. So, both of them will go off, but this one will go off very quickly with respect to this one. So, then effectively your V effective will be determined by this 1 over r term. Now, this has a minus sign before it, and k we said that this is always positive. So, it will try to be 0, but from the negative side. So, it should be look like, I mean it should look like this. So, in between these two, okay, one can do a much more detailed analysis also by exactly calculating the maximum minimum at this point, or you can simply say, okay, I can simply just by using my intuition I can add this two by saying, okay, the most reasonable thing will be that, okay, that there will be a point of local minimum, and then finally it again increases and finally asymptotically reaches 0, but always being negative, the V effective curve. Okay. So, here you see that this is the energy diagram for a particle moving under an inverse square law, and what is the most important point is that whenever you have a local minimum or local maximum, in general you have some meaning or some physics associated with it, and here what is the meaning of that? Now, here there is a very interesting difference between a true 1D motion and an effective 1D motion. In a true 1D motion, let us say if you have something like that. So, at this point, okay, so this is x and this is v of x. At this point, when the particle is having some minimum, okay, we say this is an equilibrium point, and where it is having some, for example, stable equilibrium, that we have already discussed. Now, here this is true, but and this is simply, this is just a point, this is just a point, this is a, I mean a value of displacement, certain value of displacement, but the once again in 1D. So, the motion or the trajectory is always linear motion. Okay. So, this is in a linear motion, it is simply giving us one point. Okay. So, for example, when the system is having certain energy, where it is, I mean certain potential energy, that its displacement is this one, okay, that means the systems has only one possible, I mean with this energy, let us say I am just talking about this energy E, okay, and it cuts only at one single point, and which is the point of the minimum, okay, of this curve, of this potential curve. Then if you just give this much energy to this system, the system will have only one possible displacement. Okay. So, that is the thing. Here, if I on the other hand gives the system some energy, some magic amount of energy, where exactly this energy is equal to the minimum value of the V effective, then what happens? Then basically the system has only one R possible. What does it mean? That it will only have one possible displacement value? No, it is simply saying that the system has only one value of R possible. So, in this motion the R is constant, and if in a motion R is constant, that means the system is actually undergoing a pure circular trajectory. Okay. So, that is something very important to understand. Here at this point, this is nothing but a circular trajectory with this radius equal to some r is equal to r0. Okay. Now, coming back to some other situations. So, for example, let us say you have an energy which is equal to some value over here, then again you see that your system will have a bounded motion with some r min and r max. And here, sorry, if I give you a value of energy which is here, let us say E prime, okay, then here you can say actually this is E double prime and here this is E prime, then you can simply say that the particle only has one turning point, and so the particle is not having any bounded motion. So, its r min is finite, but its r max can be infinity. Okay. So, this is unbounded motion, this is bounded motion, and this is a special case of bounded motion which is circular. Okay. Now, with all these things we can even calculate the radius of the circle and the corresponding energy for an inverse square law. Okay. So, how to calculate the radius first of all? So, we already understand that for a circular orbit, okay, we should have dV effective dr r0 should be 0. Okay. Then you can do simply the calculation just by keeping in mind that V effective is equal to L square by 2 m r square minus, I just have to check K by R, right? Yes, K by R. So, then dV effective dr will simply be equal to minus L square by m r cube plus K by R square, and that should be evaluated at R is equal to R0, R0, and which should finally vanish. Then you can simply say that okay, K by R0 square should be exactly equal to L square by m R0 cube, and my R0 will be simply equal to L square by mk. You see, this is the very fantastic result for a motion under an inverse square, attractive inverse square force. Here we are talking in terms of the attractive inverse square law. So, R0 is equal to L square by mk. L square is nothing but a constant of motion, m and k both are constant of motion. So, for a system, for an inverse square law, what would be the radius of a particle for a given inverse square law? You can easily calculate from the initial conditions, from the knowledge of constants of motion equivalently, and also from the exactly if you know the law of force. That means, if you know what is F of r equal to minus K by R square. So, that K is also a very important. Okay. Now, one can also ask that what will be the corresponding potential energy, I mean of course, the effective potential energy. So, that will be then V of R0, which must be, I would say V effective R0, which must be V effective minimum is equal to minus K by R0, right, plus L square by 2 m R0 square. Okay. Now, already we have seen that what is R0 square is L square by mk. Okay. So, I can easily write this is minus K by R0 plus L square by 2 m. R0 square is L to the 4. Let me just check. I can do another thing actually. I can do like this. I can do one thing. I can, yes, I can substitute for the first term. That will be even easier to understand. Yeah, both are actually equivalent. So, I can do one thing. I can simply write this R0, okay. I can write K by L square by mk. So, this R0 I can write L square by mk over here, plus then I also have L square by R0 square. Now, this is true that whenever you have such things, one can actually make that R0 square is L to the 4 by m square k square. Okay. So, one can actually then write that R0 square, so L square by 2 m, R0 square is L to the 4 over m square k square, and that L to the 4 and L square will go away to give me L square, and that m square will go away, and finally you will have minus m k square by L square. Then also you will have here plus m k square by 2 L square. and you will have, so this is just double of this with a minus sign. So, finally, it will have minus mk square by 2L square, which is less than 0. So, this is the total value of V effective when the particle is having its minimum effective potential energy and particle is actually exhibiting its motion in a circular orbit under an attractive inverse square law of force. Okay. And since this is the minimum value of V effective, I can always write that any V effective can always be greater than or equal to this value minus mk square by 2L square. Okay. That I can write, okay. Since minus mk square by 2L square is V effective minimum. Okay. If I write that, I can add some positive definite quantity, which is nothing but the kinetic, the effective kinetic energy of the particle, like this, and which must be greater than equal to 0, will also be then greater than equal to minus mk square by 2L square. That much I can write. Okay. This is quite easy to follow. Then I finally write E, which is the total mechanical energy, must be greater than or equal to minus mk square by 2L square. Okay. That much I can also write, and it simply gives me E plus mk square 2L square greater than equal to 0. And now you do something, mk square by 2L square, I will have 1 plus 2EL square by mk square. Okay. You see, this is something which I can write. So, I can simply take this term common from here and then I can write here. Here you have to just take a caution, this term is in general negative and this term is positive definite. The sum of these two is not a positive definite quantity. So, E can or cannot be positive, that you have to always take into account, okay, this fact. So, when I say E is greater than equal to this, it can simply be a negative quantity, but the value will be greater than how to say, like this will be simply can be negative, but it will be greater than this value, that much we can claim. Now, we can also say that if we have this, I can say another thing which is very interesting is that this is a quantity which is, you can simply see from here, m k square by 2L square, which is greater than equal to 0, actually greater than 0 you can say, because this is positive quantity. And since the multiplication or the product of these two terms, they are greater than equal to 0, that is why this must also be greater than or equal to 0. Okay. And actually we will see in a next discussion that that is completely in consistency with our geometric understanding of the trajectories of a particle under a inverse square law of force. Okay. So, before going to the details of that, let me just call this positive quantity. Since this is a positive quantity, I can always express that as a square of a real number, which I call E, and we will see that this is nothing but geometrically the eccentricity of the conic section, which is nothing but a trajectory. Okay. Already in a previous lecture we have seen that the trajectory of a particle under an inverse square law is given by a conic section, and more precisely under an attractive inverse square law is given by a conic section. So, and for that conic section we have to have some eccentricity. we will actually see that this quantity is nothing but the square of that eccentricity. Okay? Thank you.